For this video on multiple regression, we'll cover the diagnostics. We'll focus on one in particular that is very useful for multiple regression. Okay, what we're really looking for are outliers and influential data points. So outliers are those extreme values, and they stand out from the rest of the distribution because they are outliers. And what we'll talk about is outliers can either be influential, where they really have a significant effect upon the regression model or the regression equation, or not influential. They're out there, but when they're out there, they stick pretty closely to the regression, the best fitting line, as per the other participants in, say, a data set or other elements in a data set. The one that we've looked at the residual against the predicted Y value. That's really good. The one we're really going to focus on right now is Cook's D. And Cook's D is the influence of a data point on the regression equation. That's quite useful for multiple regression, because what a Cook's D is what it does is it goes through each data point, every row of data, every data point, or in the data set, and eliminates that row of data. So that one participant's data is removed from the data set, and the regression model is rerun to see what the impact of removing that person or that row of data has on the regression model. If you remove that point and it dramatically changes the slope functions, then that's a very clear indicator that that is a very influential data point. And you have to make a decision then as to what you will do with that value. And that's Cook's D. Okay. The other piece that we won't get into in too much detail is what's referred to as the DF betas. That's really, if you eliminate a participant or a subject's data, what impact does it have on each of the respective slope functions for the multiple regression? And you can derive that from SPSS. I'll show it. But if you get a DF beta for a given slope function that's greater than 1, that's something that you need to, that alerts you to basically look at that in greater detail as to why, what's going on in terms of driving the change in the slope function when you remove that given person. So once again, focus is Cook's D. If you see a Cook's D value greater than 1, I got to start looking at that data point to see what is going on. And once again, a Cook's D is you iterate through all of the rows of data or all the participants, remove a participant, rerun the regression model, see what the results are, compare them to the results when that person is in the regression model with everybody else. And then you iterate through all the participants, removing them one by one to see what influence they have on the regression model. In the example I have here, I've acquired the monthly income of very wealthy individuals, and I assess their IQ, so their intelligence quotient, see how book smart they are, how smart they are. And I want to see, does IQ predict monthly income? And these are people that are making super amounts of money. This is their monthly income. And I can see from my scatter plot that, yes, IQ is a predictor of income, monthly income for the very wealthy. And I have an R squared of 0.5, so 50% of the variability in income can be predicted through IQ. I look at my residuals, and they look fairly clean. Nice scattering on the negative side, scattering on the plus side. I do have the what I would be a bit concerned about, but I can live with that. R squared is pretty high, and it does seem to be here, so it's leveraging a bit, but not too bad. Okay. Now I'm going to change the values for participant 20. So I'm going to change participant 20 so that the value is an outlier, but it's not very influential. So I've upped the income for that person to $87,000 a month, and I upped their IQ to 150. So it is an outlier in terms of where it is. So, you know, with the average here of about 110 for IQ, I've got this extreme one that is roughly 20 points or almost 30 points higher than everybody else. And in terms of income, their income is approximately 20,000 more, or roughly 17,000 more than the top end of everyone else. So it is an outlier, but it's not a very influential outlier. And I can see that it hasn't had much of an impact on my regression equation. The slope function for the previous analysis was 972, and it goes up to 976. So the slope really hasn't been changed much, and my R square has gone up, but it hasn't gone up super dramatically. It's still fairly substantial. I can see the residual for that person actually is fairly moderate. It's fairly decent. And the Cook's D, I flag a Cook's D if the value is greater than 1. And I'm seeing here, yes, this is an outlier. It's an extremely wealthy and an extremely smart, or a person with an extremely high IQ. But it's not overly influential, even though it is an outlier. And the one that I have, the residual here of 2.5, that actually represents another individual that I'm not. It's out there, that's going to happen, but I'm fine with it. Now the next data set is going to be one where I have an outlier that is extremely influential. What I've done is I've kept the income at 87,000, but I've dropped the IQ down to 85. So this could be a trust kid. So trust kid coming from a super wealthy family. It could be some form of royalty, could be some inbreeding, I don't know, but very low IQ, but a fairly substantial income. And that point is over here. Now, that is an outlier that's extremely influential. So, the one value, remember the original slope was 972 from the original data set, no outliers. That slope has now dropped to 243. My R squared has gone from 0.51 down to 0.02. That is an extreme drop in the R squared and in the slope function. Basically, it's eliminated all prediction. And once again, it's least squares. So what happens is the line is pulled up by this point because the best fitting model is desperately trying to reduce the distance between the predicted value and the actual value. And that tilts the line, draws that line up here and tips it up, which eliminates my slope, which makes it no predictor. And I can see my residual is fairly high over here, so I can see the residual here. And what I can really see is the Cook's D. When I take this person out of the regression equation, that regression equation stabilizes, and that influence is gone. And that's why my Cook's D, any Cook's D greater than 1 is cause for concern. Now the question is, what do I do with that data point? If I have no real valid reason for eliminating it, I can't get rid of it. I just have to, in a sense, live with it. I could do data transformations to try and dampen the impact of it, but I wouldn't be comfortable ditching the data. Now, if I had a valid reason for eliminating it, I could look at really what population I'm sampling from. So if I'm sampling from, let's say, people who are first generation wealthy. So let's say, okay, everyone in here is kind of like an Elon Musk or a Bill Gates or a tech person or someone from pharmaceutical who is first generation wealthy or super wealthy. I could take those, and our income would be a lot higher. And then, but if I have a half-wit royal in here from a royalty from some country, I go, oh well, that's established wealth. They've had many generations of wealth that's been inherited from one generation to the next, and then they have a half-wit son, and you have to say, okay, then you know what? If it doesn't represent the population of interest and the population that was sampled, and it was included for reasons that it shouldn't have been, that there was a mistake in the methodology in terms of the sampling, then possibly you could say, okay, I could eliminate it. But if you're going to do it, you would run the analysis twice. And say, okay, here's the analysis with the half-wit included. Here is the analysis with Prince half-wit eliminated. And at least alert your audience to the analysis that you did. And that pretty well covers it for regression diagnostics. Oh, multicollinearity, I'll get that in the next video.